Okay, now I will discuss with you the third homework, and it is DNA force extension. Okay, so it is on your UBS course page. It shows up on under homeworks, and the due date is 20th of August. You can check it. Okay, so this is the report template of your third homework. It's flow stretching and DNA extension. And again, we're going to use a simulation for this. We're going to, by using a flow technique which is called flow stretching, a linear strand of DNA is, tethered to a planar surface at one end. It is a microbed or microsphere. It is attached to microsphere at one end. It is fixed at the other end, and then by flowing a fluid over this microsphere, there is going to be a drag force on the microsphere, and this microsphere is going to pull or extend, try to give attention to the DNA. So when the flow is large, of course this extension is going to be large. It's going to look like you're stretching or you're trying to expanding, pulling a rubber band. Okay, and you will see how. So by doing some experiments, some measurements on the simulation, we will be able to understand how the DNA stretches against the flow. And again, it starts with some preliminary questions, and first one is, what is the force versus extension curve look like for a rubber band? What we mean by extension is, if you take a piece of rubber, I don't have a rubber at my hand, no. So imagine that this is a rubber band, okay? So if this is a rubber band, just without applying a force on the rubber band on both ends, measure its length. But if you pull it, you extend it, right? You expand it, and then there is going to be force on your hand, of course, because of the expansion. And measure this extension length, and just feel how much, qualitatively, what's the force value on your hand. If you extend more, you will see that the force is going to on your hand is going to be more, but the extension, of course, again, length is going to be more. So this is under extension how the rubber band will look like. You'll just give a rough sketch on over here. Just press it, paste it over under this question. So this is your preliminary question. The second one is, what do you think the force versus extension curve for DNA? Okay. Well, DNA is a stringy-like structure, but it's a molecule, right? But the molecule is composed of some a bond of atoms which are stick together with some chemical bonds. Well, can you extend the chemical bonds when you pull the atoms? Of course you can. It's there are models that explains this expansion of materials. When you expand a material like a rubber, of course, what happens inside the molecular level is that the atoms and molecules that forms the rubber will move apart from each other, right? Because you're pulling it, but doesn't break. Okay, it doesn't break. Just the distances between the atoms of the molecules will increase. So you might expect that DNA will behave like this in the case of a rubber band. When you just pull it, it will extend. And pull more, it will extend more. Of course, there is going to be a breaking point. You cannot just infinitely extend it and infinitely stretching the DNA. So this is what you expect from DNA. And what about the procedure? Well, for the procedure, again, you will run the simulation, which is given on this web page, and I just downloaded it onto my computer. let me run it. It is DNA, stretching the DNA. This is the file, and just run it over on your computer. Your computer must have Java. So initially, this is your screen, what you see over here. Again, there is this optical tweezer. The optical tweezer trapped this bed on over here. Well, this end is fixed. Well, as you see, this end, it doesn't look like a molecular motor, but because it's not pulling, it's just a fixed part. It's not like pulling something, but it's just nailing one end of the DNA over here at a fixed position. Well, we'll again disable the Brownian motion for this simulation, and you can play with the repositioning the optical tweezer's focal point by dragging it toward left and right. Okay, and if you drag toward right more, eventually because the extension on the DNA will increase and the force will increase, this force will take the bed out of the trap. Okay, when you pull it more and more, when you try to extend the DNA more and more toward right, so you see there is this dislocation of the bed from the center of the trap. So eventually it will just when you pull more, it will just make off center, and then it will go away from off the center or off the trap. But we're not going to work with the optical tweezer with this experiment. On this experiment, we're going to just turn the laser off. And how then in that case, how are you going to extend it? We are going to extend it by controlling the fluid flow. Again, you can press on these boxes on the right, and at the bottom, very bottom, you will see the fluid controls. Okay, is there any way of increasing the fonts over here? I am not. Preferences, maybe. No, there is no way. Okay, but anyway, you can see these small scripts by enlarging your screen. Make the video full screen to be able to see it. So what happens when you give some flow from left to right? Of course, this flow will produce a drag force on the bed. You see, I just give some flow speed of 145 micro per second, and now because of this flow toward right, there is going to be a drag force on the bed, and this drag force, just keep the bed in this direction, but it will extend at some distance, but eventually it will stop because DNA is now stretched. Of course, if you give more flow speed, you will extend it more, right? I mean, just increasing flow speed around 209, so it's extending more. Well, what about seeing this drag force on the bed? Again, there are these force boxes over here on the right hand side, so you can just show. You can click on the checkbox of show fluid drag force. So if you click on this, where my force is very small over here, as it shows there, but it's small. If also check the force value, now I just read the force value to be 3.48 times 10 to minus 1 piconewton. So there is a drag force of this much on the bed, and the bed is at a fixed position now, but the DNA is extended. All right, so it is extended with some distance, but you can always measure the distance with respect to some reference point. Let's respect the reference point of this fixed point and just run the histogram. Okay, histogram. Well, histogram measures the position of the bed. It doesn't nothing to do with this fixed point, but what you can do is you can use this ruler when you show the ruler on the boxes. just bring it over from this end, which is 0, to the position of the bed, center of the bed. It shows like 1800 nanometers almost. I mean, I think it's a little smaller than this, but this is my resolution. So you can measure always the position or extension, the total length of DNA under this flow speed, etc. So if you decrease the flow speed, of course, the extension will be less. And extension now this time like around 1000. I'm just trying to bring 1400. Yeah. So with this flow speed of 87 micron per second, and with the force value of 1.45 times 10 to minus 1 piconewton. So you can measure the force, drag force. You can see the flow speed over here, and you can measure the extension length of DNA. So these all you can do. All right. Okay. So what are you going to do? These are the tools that. What happens when you do this? When you do what? It was originally it was the optical tweezer was on, and the bed was on the trap point. But when you just turn off the optical tweezer, what happens? This is the question that you are going to answer on this over here. And the third, the black line segment connected to tag to the bed of the represent DNA. So this line, represents DNA. Is DNA static or fluctuating? Explain why it behaves the way it does. So, what you see clearly over here, that this DNA is fluctuating, it's jiggling around. And you're going to answer why this is so. Of course, this very jiggling very much. Why? Because of the Brownian motion. You see, when since the fluid is in liquid form, and in the liquid form all the atoms of the liquid collide with the molecules of DNA, and because of this there is this jiggling around. So what about the bed position? Is static or fluctuating? But since we disabled the Brownian motion for the bed, it's not fluctuating. But if I enable it, also bed will fluctuate. Okay, you see now it's fluctuating. But the fluctuating bed, it is very hard to measure its location. But one thing is that you see, by running this position measurements, the DNA, the bed is jiggling around this axis, which shows the 0 line. And you see all these measurements, it's sometimes over there, and sometimes over the right, and sometimes over the left of the 0 line. But once you disable Brownian force, the bed will relocate itself again to a fixed point. So, alright, so our first measurements will not include Brownian motion, so I just turned it off and disable it by using the control panel. And in this step 5, we will now use a fluid drag force to extend DNA. I just provided some flow speed, and then the bed is now at some distance away from this fixed point. The controls are in the fluid drag force, the other force values, and the ruler. Okay. And next, independently try to develop a procedure to measure the force extension curve of the DNA using the controls you have just learned. It is recommended that you collect no less than 8 data points. Check your procedure with your instructor before proceeding. And this part you're not going to do. Of course, I'm not present in a class. So one thing that I can suggest over here what to do. Try to develop a procedure to measure the force extension curve using the controls you have just learned over here. So I in fact I have just told about this just previous in at the beginning of the simulation. I just told about this. You can measure the extension of the DNA by just doing this. Okay, just bring this dashed line, the axis, optical axis of the tweezer, and from here to here just measure the extension. That's it. This is the way you extend, and you can change the flow speed. Extension will be different now, and again measure it. So this is the way. I mean, you can just collect 8 data points. Well, you can always read, for example, for this value of flow speed, the force is 2.13 times 10 to minus 1 piconewtons, and its flow speed is 128 micron per second, and the extension distance is just around 1600. Okay, so all these you can measure, and you change the flow speed, and the extension changed now. The extension is just over some 1200 nanometers, and the force is 1.17 times 10 to minus 1 piconewton, and the flow speed is 7 t micron per second. So this is the way. I mean, this is the way you can measure it. Now perform your these. What I told you, that the these measurements with different flow speed. Just measure the DNA extension and measure the drag force in piconewton. So let me do this for you for 2 points. Okay. Let me come over here again. So I will just start with let's say 50 of 50 microsecond fluid flow. And with 50 microsecond flow, since it's 50, I just type it over here, 50. And what about the DNA extension? DNA extension is just, I measure from this point, it is 0 line, to the location of bed, and it is over 1000. It is 1000, between 1000 and 1200. And it is this 1, 2, 3, 5 parts between 1000 and 120, 1200. So it's around like if you divide this by 5, the center is around like 1050 or 1060. Let me write this as 1060. You can do this better than me. 1060 nanometers or so. What about the drag force? Okay, drag force is, as far as I can see, it is 8.33 times 10 to minus 2 piconewton. It's hard to see. 8 times 32 is 8.32 times 10 to minus 3 piconewton. Okay, so that's it. Sorry, it's 2, not 3. So this is the first data row, and for the second one I just increase the flow speed to 100 micron per second. Okay, it comes to now with the 100. I just type over here 100, and let's measure the extension. It is over 1400. It is between 1400 and 1600. Again, this is like add 50 more or 60 more. Like it is around 14 and 60. It is 1460 nanometers. And what about the force? I am just reading the force to be 1.67 times 10 to minus 1 piconewton. 1.67 67 times 10 to minus 1 piconewton. So you will go like this, okay? I mean, you just increase. I just increase 50 by 50, but how many data points? When you have, at least you must collect 8 data points. If you give different flow speed, try to be the bed to be on the screen, because if you give more flow speed, it's going to be go away from like maybe 200 or 500. Well, it's going to be inside the screen anyway, no problem. So I can collect this 8 data points. These are the first 2 that I made for you. And what you're going to do is you're going to analyze this. What about the analyze part 2? For this part, you will produce a graph of the applied force versus DNA extension. So again, you can use Excel or Tracker to do this in your data. Okay, the graph of extension on the horizontal axis. The extension is going to be horizontal axis, and the force is going to be the vertical axis. Okay, so you'll plot this graph, and this part is you compare your data to that's supplied by yours. I will not supply any data, but I will check it anyway. So this part is just I will check. Do this plot. So answer the following questions. Once you have done making the plot, is your graph similar to what you predicted for DNA? So force versus extension. I mean, force versus extension for rubber kind of things like springs or rubbers, etc. Force versus extension goes like a straight line graph. Okay, let me show it to you. Force versus extension. Okay, this is the force axis, the vertical axis, and this is the extension, or let's say x, whatever. Normally, I mean, for rubbery kind of materials or spring-like kind of materials, this graph will look like a straight line graph. Sorry, a straight line graph like this. Well, it doesn't look like straight, but I'm not. Okay, it's this kind of graph, and well, of course, the slope might be large or small. It depends on the hardness or hardness of your material. If it's hard material, the slope is going to be large. If it's soft material, it's going to be small. So you will check that your plot will look like this. I mean, there is going to be data points over and over. So if you make a baseline to fit this data, does it look like a straight line? This is the question that you will answer. It should look like a straight line, but anyway, you will check it. And next, does DNA behave similarly what you expected from a rubber band? If it's a straight line graph like this, then yes. What do you think? What do you think this is? Is the contour length of the DNA? What do you think is the contour length of the DNA? And how is the extension of the DNA related to the contour length at high force? Well, if you provide the highest flow speed, it's going to be high force. But sometimes what happens is that if you, for example, for a rubber or for a spring, for small forces, the curve will go like this. But if you increase force, eventually the curve will look like this. You supply you extend it more and more, but the force is not going to change. Extension will be increasing, but if you go over some maximum value of force, this extension will not linearly proportional to the force anymore. So I mean, at this point, the elasticity of your material will break down. So do you expect this kind of behavior from DNA? And you will do this, okay? You will do this. You provide the more drag force and very larger drag force, and does it behave like this graph, the DNA? So you'll answer this. Does DNA obey Hooke's law? And this is your job to answer this question. I'm not going to go over it. So part 3, there is also